Good afternoon, everybody. Professor Ayorinde reaching you from Abuja, the capital city of Nigeria. I do know that to those of you in Washington, D.C., it is 8 o'clock in the morning. I understand that it is raining and it is very cold at this point. So I do want to welcome all of you for joining the session today. In today's session, we are going to go over some of the questions in preparation for the final examination that you guys are going to be taking tomorrow. That is Wednesday, December 10, 2014. So at this point, I will be acknowledging those of you who have already joined us. We do have a lot of material to cover today. For today's session, we are going to use a previous final exam from Dr. BAKARE for the session today. And because of that, I know that some of the questions we have done before, so we are essentially going to do the following questions. We will be doing question 9, 11, 12, 13, 15, 16, 17, and 19. I hope we can cover most of these problems. This is a lot of problem indeed, but as much as we can, let us see what we can with respect to covering most of these questions here. To get the session started, I am going to call on Ayana. We are going to go to question 9. Question 9, of course, it is a question that deals with reactions and reagents. So therefore, Ayana, can you read question 9 for us?
Give structure of the major organic product in the sequence of reactions below. Show stereochemistry where appropriate.
Okay, thank you very much. And of course, this set of questions here, this is what I call an icebreaker question. In other words, this is a set of questions that will get us started because I do expect that most of you will have an answer to each one of the questions here. Okay, so let us get started on this. Okay, what you have here, we are supposed to give the structure for the major organic product in the sequence of reactions below. Okay, so we are starting with this compound here, which is a secondary alkyl bromide, and then we are supposed to react that with potassium hydroxide in the presence of ethyl alcohol as solvent. Now, does anybody know what kind of product are we going to get here? Just let me know whether it's going to be an alkyne, an alkene, a carboxylic acid. You could send me your answer to the chat window or pick up the mic. Okay, what would be the answer to this question? Reacting, an alkene, excellent. That is Kessler. Okay, Kessler, you are welcome. Okay, also Chelsea say 3-eptene, you are also welcome. Okay, very good. All of you are correct. So we are going to get an alkene. So therefore, let us write the structure here. So essentially, we will get this here. Okay, this 1, 2, 3, 4, 5, 6, 7. Okay, so we are going to get this alkene right here. Okay, so let us number this alkene, that is the product. Take this out of here. Okay, let us call this carbon 1, 2, 3, 4, 5, 6, and 7. Okay, if you notice here, from the starting alkyl bromide, we have carbon 1, 2, 3, 4. The bromine atom is attached to carbon number 4, and then 5, 6, and 7. So what are we doing here? We are forming a bond between the carbon-carbon bond between carbon 4 and carbon 5. So this type of reaction is what we refer to as dehydrohalogenation. Okay, very good. So now we got compound A. Now we have gotten compound A. Let's take this out of here. So we have compound A at this point, which is this here, this alkene. Now, they now want us to react the alkene with hydrogen in the presence of palladium and using ethanol as solvent. What would be the product? What would be compound F at this point? What would be compound F? What are we doing here? Ethane. Very good. Excellent. Okay, Chelsea say ethane. Excellent. Very good. So therefore, we are going to do hydrogenation. In other words, we are adding one hydrogen to carbon 4 and another hydrogen to carbon 5. So therefore, we get what we call hydrogenation. So we are going to get this product here. Okay. Notice here we are going to get hydrogenation. We call this hydrogenation. Okay, folks, I just lost my internet very briefly. That is during the course of this presentation. By the way, if I lose my internet, you guys will just stay online. I will get right back with you. Okay, as I was saying, now we are supposed to take compound A again and react compound A with chloroform in the presence of potassium hydroxide to get compound B. So what are we going to get here for compound B? What is happening here? What does chloroform do with a chloroform in the presence of potassium hydroxide? What will it do with a carbon-carbon double bond? Okay, excellent, excellent. So we are going to form a 3-member ring, cyclopropane ring, with 2 chlorine atoms attached to one of the carbon atoms. Excellent. So therefore, this will be the product. And that is compound B. 1, 2, 3, 4, 5, 6, 7. So this is our compound B right here. So in essence, this reagent here, what it does is to add a carbon atom to a carbon-carbon double bond, so that that carbon atom is also attached to 2 chlorine atoms. That is what this reagent will do. Excellent. Okay, so now let us continue. How about compound C? We are supposed to react osmium tetroxide followed by sodium hydrogen sulfide with a carbon-carbon double bond, with this carbon-carbon double bond here. So what do we expect to get? What does this reagent give you with a carbon-carbon double bond? 1,2-diol. Excellent. Very good. Very good. I think you guys are ready for your exam tomorrow. I could see from your answers here. So we are going to get a 1,2-diol. Now, what is the stereochemistry of that 1,2-diol? That is correct. But what is the stereochemistry? Ayana also said diol. Very good. What is the stereochemistry? Is it going to be? Are they going to be? Yes. Syn addition. Okay. Excellent. Okay. So this is what we are going to get. So the product will be this here. Okay. Let me do this better than that. Okay, so we are going to add OH, another OH. You notice the stereochemistry here. This is a syn addition reaction. And what are we doing here? We are adding two hydroxy group across the carbon-carbon double bond. One hydroxy group is added to carbon number 4 right here, and another hydroxy group is added to carbon number 5, and that is how we got these products here. Now the point to be made of this is that this reagent here, what it does is to add two hydroxy group across the carbon-carbon double bond, such that those two hydroxy groups will be cis to each other. So we call this a syn addition reaction. Syn addition reaction. Okay, very good. Moving right along. Okay, let's take this out of here to make this a little clearer for everybody. Okay. Now, at this point, we now want to take compound C, which is this here, which is this 1,2-diol. We want to take this, and then we are supposed to react with, oh, I did cover that up. Sorry about that. Let me take this out of here. Okay, now we are supposed to take compound C, which is this here, and react with periodic acid in the presence of water. Okay, so what would that give you? So periodic acid reacting with a 1,2-diol, what kind of product do you expect to get here? What kind of product does this, what does this reagent do with a 1,2-diol? What does this reagent do? Two aldehydes. Excellent, excellent. Two aldehydes. In other words, we are going to cleave. Okay, what that reagent will do is to cleave the carbon-carbon double bond. In other words, to cleave the bond that joins the two carbons containing the hydroxy group, such that each one of those carbon atoms becomes an aldehyde functional group. Okay, so let us see. That is why we are going to get two compounds here, D and E. So what are those two compounds? Let me go ahead and write this here, take this out of here to give ourselves some space. Okay, so we are going to get this here. Okay, so if we cleave this at position 4 and 5, we'll put numbers there. If we cleave this at between 4 and 5, okay, that means on this side, we are going to get 3 carbon atoms, and on this side, we get 4 carbon atoms, the end of which we have an aldehyde functional group. So what is the answer here? So that would be this here, 1, 2, 3, 4. That is one product. The other product will be this. Okay, so therefore, compound D and E will be this here. Compound D and E will be these two products here. Any one of them could be the D and the E. Okay? Okay? So therefore, what do we have here? The point of this exercise here is to know what these reagents do. In this particular instance, periodic acid, which is this here, in water, will cleave a 1,2-diol such that you get 2 aldehydes. Very good. Okay, now let us continue here. Now we are supposed to do, let me move this up. Let me move this up a little bit. Okay. Okay, good. Now we're also supposed to take compound A. We are supposed to take compound A and react compound A with bromine in carbon tetrachloride as solvent in order to get compound I. What do you think will happen here? What is happening here? Bromine reacting with a carbon-carbon double bond. What do you expect to get? Bromine reacting with a carbon-carbon double bond. What do you expect to get? Okay, Grignard dihalide. Excellent. Anti-addition. Okay? Anti-addition. In other words, we are going to add 2 bromine atoms across the carbon-carbon double bond. 1 bromine atom will go to carbon 4. Another bromine atom will go to carbon 5, such that the 2 bromine atoms will be trans to each other. So therefore, what is the product going to look like? To look like this. Let's see here. So we have 1, 2, 3, 4, 5, 6, 7. 1 bromine will go here. The other bromine will be here. In other words, you are going to get a trans addition product. You are going to get a trans addition product in which the 2 bromine atoms will be trans to each other. So therefore, let me write this a little better than that. Okay, be trans to each other. And that would be the product that we call product I. And that is I, this one here. Okay, very good. Okay, the last question in this series of questions here. Okay, now we are supposed to take, let me take all of this out of here, just to clear the screen. Now we are supposed to take once again compound A. We take compound A and react compound A with potassium permanganate in dilute acid. 1 potassium permanganate in dilute acid. Now what will happen with potassium permanganate reacting with a carbon-carbon double bond? What do you expect to get here? What do you expect to get here? Potassium permanganate reacting with a carbon-carbon double bond. A 2 carboxylic acid. Excellent. Cleavage. Okay, Kessler said cleavage. Excellent. Chelsea said 2 carboxylic acid. Both of you are correct. What that reagent will do is to cleave a carbon-carbon double bond. To cleave a carbon-carbon double bond right here. Okay, such that each carbon of the carbon-carbon double bond, if each one of those carbon is attached to an hydrogen atom, will become a carboxylic acid. Keep that in mind. You only get a carboxylic acid if any one of those, if each one of those carbon is attached to an hydrogen atom. Now, if one of the carbon is not attached to an hydrogen atom, then you get the carbonate of a ketone. So keep that in mind. So in this case, what are we going to get? We get this product here. 1, 2, 3, 4. Okay, so we get 1, 2, 3, 4. And then on this side, we get 3. 1, 2, 3. Move this up a little bit. And then we get this here. Okay? Those are the two carboxylic acid, G and H, that we are going to get with this reaction. Now, the point here is, anytime potassium permanganate reacts with a carbon-carbon double bond, you will clip the carbon-carbon double bond such that you get two carboxylic acid, provided that each one of those carbon atoms, or any one of those carbon atoms, is attached to an hydrogen atom. On the other hand, if any one of the carbon atom is not attached to an hydrogen atom, then you have that carbon atom becomes the carbonyl of a ketone. So keep that in mind. For example, if you have this, right, and you do potassium permanganate, okay, what do you get? This carbon here will become the carbonyl of a ketone, and this carbon here becomes the carbonyl of a carboxylic acid. So in this case, you are going to get this. Okay, so that is what you get with that in this particular instance. Okay, so let us go to the next question, number 11. Okay, can I get Chelsea? Can I get you to read this question for us, if your mic is working? Oh, okay. Your mic is not working. Okay. Okay.
Show the structures of the organic products expected when cis-5-pentadecene reacts with each of the following reagents.
Okay, thank you. Once again, this is a case of knowing your reagents. So what they are testing here is whether you know your reagents and what those reagents do. Okay, so let us start with the molecule here. Cis-5-pentadecene, cis-5-pentadecene, and then we are given a series of reagents to react with that. So the first thing we need to do here is to write the structure for cis-5-pentadecene. Let me move this a little bit so that we have some room here. Okay. So we have this here, cis-5-pentadecene. So that means this has 15 carbon atoms. So you have, let us have this here. Okay, that is 3. And then here, since we are dealing with cis, okay, so folks, for the purpose of this discussion, since we are dealing with a symmetrical molecule, I'm going to simply refer to this part of the molecule here and this part of the molecule here as R, okay? Okay? Just for the purpose of this discussion. So now, what is the first reagent that we need to use here? Let me bring this back to focus. Okay, what is the first reagent that we need to do to use? They want us to react borane followed by hydrogen peroxide with this reagent. Okay, what will be the product? What does borane do? Let us simply write that reagent here, borane, which is essentially BH3, which is step 1, and then you follow that up with step 2, hydrogen peroxide in basic medium. Now, what does this reagent do with a carbon-carbon double bond? Can anybody tell? Okay, X, exactly. Anti-Markovnikov addition of water. Anti-Markovnikov addition of water. Very good, that is correct. In this case, however, this is a symmetrical molecule, so therefore, the hydrogen could go to any one of those carbon atoms, and the hydroxyl group could go to any one of those carbon atoms. Okay, what is the stereochemistry? What is the stereochemistry? What is the is it going to be, are those, the hydrogen and the OH, are they going to be cis to each other, or? Okay. Oh, I'm sorry, pentadecene. Okay, I think let me see the question here. You say pentadecene. Oh, I got it. Let's see, we have 5. No, this is low decene. Let me make that correction. They do want us to do pentadecene. Let me do this. Thank you so much for letting us know that that was an oversight. So this one here will be, take the 3 out. So we take the 5, take this out, take this out. Okay, so we are going to have 5. Let's put 5 here. Okay, so that is 6. If we put 5 here also, so that would be another 6. So that is 12. Okay, so this therefore will be 6 right here. Okay, is that correct? 5, 11, and then you have 4. Okay. Okay, so this is correct. Therefore, yes, this is not actually a symmetrical molecule, as I was saying. But if you look at this, what we have here, we are going to add hydrogen to here and hydroxide here, but it could go both ways, since in this case, each one of them only has one hydrogen attached to it, so therefore we are going to get a mixture of products. So let us just give one product here, okay? So we are going to get this. Like I told you before, I'm going to call all of these R to save us some time here. So this will be here, here. We say this is R, and we say this is R. Okay, let's call this R prime, and we call this R, and therefore the hydrogen will be we could have the hydrogen here that is added, and the hydroxide that is also added, showing the stereochemistry right here. And of course we have hydrogen here and hydrogen that was there before. So this reagent, borane, followed by hydrogen peroxide, what it does is to add one hydrogen and one hydroxide across the carbon-carbon double bond in order to get a syn addition product. So this is a syn addition product, in which case you have the two groups that are added, the hydrogen and the hydroxide are on the same side of the molecule. Okay, very good. How about B? Let us go to B, M-chloropabenzoic acid. M-chloropabenzoic acid. Let us see, what does that give us? B, M-chlorobenzoic acid. With this reagent here, what does it give us? Oh, epoxide. Okay, very good. Epoxide. So let me move this a little bit here. Okay, so that will give us epoxide. So let us say we have this here. Once again, I'm going to refer to, Once again, I'm going to refer to this group as R, and this one is this is R prime, and this is R. So therefore, what do we have? We have R prime and R, and you guys already told us we are going to form an epoxide. Okay, to form an epoxide, and the hydrogen that was there before is still there. So that hydrogen is here, and that hydrogen is here. So in this case, what the reagent will do, M-chlorobenzoic acid, what it does is to add one oxygen atom across the carbon-carbon double bond, okay, so that we form an epoxide. So this becomes what we call an epoxide. So this is a case of knowing your reagent. Okay, once you know your reagent, what I keep telling students is knowing your reagent is the beginning of knowing organic chemistry. Okay, now let us go to C. Let us go to C. Okay, so by the way, this is, for clarity, let me make this clear here. This is the answer to B, and this one is the answer to A, just for clarity, okay? Okay, now let us go to C. Let me erase some of what we have here. Okay, let us go to C. For C, what do they want us to do? Okay, the reaction of concentrated potassium permanganate followed by acidification. I'm sure you guys already know that. In other words, potassium permanganate reacting with a carbon-carbon double bond. What do you expect to get? Let me take this out of here. What do you expect to get? Potassium permanganate reacting with a carbon-carbon double bond. What do you expect to get? I know that all of you know that already. We did that already today. Carboxylic acid. Excellent. Excellent. In other words, we are going to cleave. What that reagent will do is to cleave. Let me use another pen. Is to cleave the carbon-carbon double bond right here. Is to cleave the carbon-carbon double bond. In this case, we are going to get two carboxylic acids because each one of these carbon-carbon double bonds is also attached to an hydrogen atom right here and right here. Okay, so we are going to get two different products. How many carbon atoms in each one of the products? That's 1, 6, and 7. The other one will have 8. Okay, so therefore we get this. One, 2, 3, 4, 5, 6, 7, 8. So we get that product, and the other one will give us this here. 1, 2, 3, 4, 5, 6, 7. Okay, so we get two carboxylic acid. So therefore, this is the answer to C right here. This is the answer to C. Just for clarity, this is the answer to C. Okay? Okay, moving right along. Okay, about D. How about D? This one here. Hydrogen and platinum. What do you expect to get? I know that you guys already know that. Hydrogen and platinum, what do you expect to get? It's a carbon-carbon double bond. What do you expect to get? Carbon-carbon double bond, hydrogen and a catalyst. What do you expect to get? Okay, let us see here. Hydrogen in the presence of a carbon-carbon double bond. What do you expect to get? What do you expect to get? Okay, that is A, so therefore, we are going to get okay, folks, I just lost my internet connection very briefly there. Okay, so we are, as I was saying before, now if you hear me, give me a happy face. If you can hear me, give me a happy face. If you can hear me, give me a happy face. Okay, very good, very good. Okay. Okay, so before I lost my internet connection there, we were discussing question D, which is this here, hydrogenation of a carbon-carbon double bond. And you guys told us that we are going to get hydrogenation. In this particular instance, we will get pentadecane. So therefore, the product will be this. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, and that will be the product of this here when you react hydrogen with in the presence of platinum or any catalyst, you get that, and so therefore this is the answer to question B. Okay. Okay. How about E? How about E? Question E. Question E. This here. Hydrogen and bromine gas. What do you expect to get with that? With a carbon-carbon double bond? What do you expect to get with a carbon-carbon double bond? Okay, 5-bromo, hydrogen, okay, hydrogen bromide, excellent, hydrogen bromide gas, very good. In this case, this would be a Markovnikov addition, but it doesn't really matter because each one of the two carbon atoms of the carbon-carbon double bond is attached to an hydrogen atom. So you are going to get a mixture. So let us just deal with one of the products. Okay, so we have, I'm going to use R to represent the alkyl group. So therefore you are going to get this here. If we say we have this here, we have this here. Our R prime is here. R is here. Keep in mind, I told you guys earlier, this part of the molecule, we call this R prime. I'm sorry, we call this R, this alkyl group here. And this other alkyl group, we refer to this as R prime, okay? And that is what I have here. So, what are we doing? We are essentially adding hydrogen and bromine across the carbon-carbon double bond. And there is no stereochemistry here because we are going to get a mixture of products. So you get the bromine will be here, and hydrogen could be here, and the hydrogen that was there before is still here, which is this here. Sorry about that. It's this here, and this here. These are still there. So that this is the product for the question number E or letter E. Okay, this is this one here. Okay, that is E, the answer to E. So the answer to E, in essence, hydrogen, bromide gas, all that does is to simply add hydrogen and bromine across the carbon-carbon double bond. Okay, very good. How about F? How about F? What do you get with F? Yes, that is correct, Chelsea. You say 5-bromopentadecane or 6-bromopentadecane. That is correct in this in the question of the answer to question number E, which is this one here. We are going to get a mixture of products. Okay. How about F? How about F? Chlorine gas reacting with a carbon-carbon double bond. What do you expect to get? Chlorine reacting with a carbon-carbon double bond. What do you expect to get? Anti-addition, exactly. Anti-addition of 2 chlorine atoms. Okay? Very good. Ayana said anti-addition. Okay, Dominic said, okay, actually gave the product, we're part of the product. Chelsea said, that is dichloride. That is all correct. So in this case, you are going to get an anti-addition of 2 chlorine atoms across the carbon-carbon double bond. So if we use the symbol R to represent the alkyl group, the product will be this. If we say R prime is here and R is here, okay, therefore we are going to say now that the 1 chlorine atom is going away from us, another chlorine atom is coming at us. Another chlorine atom is coming at us. Okay, of course, the hydrogen that was here is still here. Okay, so you have an anti-addition of 2 chlorine atoms. Yes, go ahead and ask your question, Chelsea. Chelsea, go ahead and ask your question, okay? Okay, no question. Okay. Okay, anyway, so what this chlorine gas will do to a carbon-carbon double bond is to add 2 chlorine atoms across the carbon-carbon double bond such that each one of the chlorine atoms will be trans to each other. If you notice here, this chlorine atom is going away from us, and this chlorine atom is coming at us, so that is an anti-addition of those 2 atoms. Okay, the question that Chelsea is asking, let me read the question for everybody. If we are dealing with an alkane, do we have to show wedge and dashed line even if they ask for stereochemistry? Yes, you have to. Yeah, you have to. Because, you know, don't forget, you could get a case of the stereoisomer, you could get enantiomers. You could get enantiomers or there are stereomers. Yes, you have to do that. Okay, in order to show that in order to show the stereochemistry of that reaction. Okay, let's go to the last one on this series, G. Let's go to the last one on this series, G, which is this here. G is giving us this reagent here, chloroform in sodium hydroxide. Okay. Chloroform in sodium hydroxide with a carbon-carbon double bond. What do you expect to get? I think we've done this already today. with a carbon-carbon double bond. Okay, dichlorocarbon. Okay, very good. So you are going to form a cyclopropane ring system in which the chlorine atoms will, in other words, you are going to add a carbon atom across the carbon-carbon double bond such that the two chlorine atoms will still remain on that carbon. Okay? If we use R to designate the alkyl group, so we say we have R prime is here, and R is here. So therefore, in this case, we are going to have a cyclopropane ring. Okay, so this is a cyclopropane ring system, and essentially what you are doing here, what we are doing here is adding this carbon here to a carbon-carbon double bond, such that that carbon still contains the is still attached to two chlorine atoms. And that is what this reagent will do for you. That is what this reagent will do for you. Anytime you see that. Okay, let me also indicate that you will see have the hydrogen here and the hydrogen here. Okay? Okay, folks, we have finished question 11. Let us go to 12. Let us go to 12. Is there any question on this? Okay, okay, let us go to 12. Okay, if your mic is working and you have not spoken to us today, can you go ahead and read this question for us? Question 12.
Outline a reaction scheme to show how you would synthesize dodecanol starting from acetylene. Include all reagents at each step and show structure of all intermediates leading to a product.
Oh. Thank you very much. That was Kessler. Okay, very good. Thank you. Okay, so what is question now? At this point, we now want to begin to deal with a synthetic problem. If you notice here, we started with those reactions and reagents. Now, everything we did with those reactions and reagents, now we have to begin to use the knowledge of those reactions in the synthetic problem. So this is a slightly more difficult problem indeed. Okay, so it says outline a reaction scheme for the, to show how you will synthesize dodecanol starting from acetylene. Okay, include all reagents at each step. In other words, they want you to give a synthetic scheme. Okay, so the first thing we need to do here, we need to know the structure of dodecanol. Okay, the structure of dodecanol, which is this here. Let us say dodecanol is this. It has 12 carbon atoms, and it is an aldehyde. So therefore, let us simply just do it this way. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, that is dodecanol, 12 carbon molecules. So when you have a problem like this, keep in mind they want you to start with acetylene. They want you to start with acetylene. So what you need to do here is to do what we call retrosynthesis. In other words, you want to go backward from the product to the starting material. Okay, so that is what we are going to do. When you do that, you take one step at a time. Take one reaction step at a time. Okay, so let us do that. I do need your assistance here. Okay, the question that I have for you, based on your knowledge of organic synthesis at this point, of all those reagents, what one single reaction can you perform to give you an aldehyde? Can anybody tell me? What single reaction can you perform that will give you an aldehyde? Oh, potassium permanganate. Okay. Just give me the reagent. Give me a reagent. Okay. Okay. To make the double. Okay. Make the double bond. Okay. You guys are almost correct. Yes. Okay. What we need to do here, the one single reaction that you could perform, to do that, you could go here. Okay. Let me at this point, let me use an R group to represent the long alkyl chain, okay? If you're going to permit me to do that. So let us say R. Okay? If we take a terminal alkyne, which is what we have here, a terminal alkyne, what reagent do you need in order to convert a terminal alkyne to an aldehyde? Okay, yes, Chelsea said terminal alkyne. Very good, excellent. Okay, yeah, you do aboration, exactly. You do hydroboration, yeah, that is correct, Chelsea. Okay, let me give the reagent. So once again, this is a question of knowing your reagent. Once you know your reagent, when you get to synthetic scheme, it makes it very easy for you to see what you need to do. Okay, but the first thing you need to do, you need to know those reagents first. Okay, so we have borane, followed by hydrogen peroxide in basic medium. What that will give you, it will take a terminal alkyne to an aldehyde. Okay, very good. Now, then the next question I have for you is, how then do I get a terminal alkyne? How do I, one reaction that will give you a terminal alkyne? Okay, keep in mind, let us now say here, one reaction that will give you a terminal alkyne. Can you do an SN2 reaction? What kind of starting material will you need? A reaction that will give you a terminal alkyne. Okay, so far we have 2 carbon here on the alkyne, on the terminal alkyne. So therefore, we need how many more carbon? 10 carbon atoms on the R. So this R contains 10 carbon atoms. So therefore, let us see the next step. What can we do? We could do this. Supposing we do this. Okay, we take an alkyne. Take the acetylide ion, okay, and then we do an SN2 reaction using the appropriate alkyl halide. So therefore, here, let us use our R again. No, let me change the color of that. Our R could be this here. In this case, let me call this R prime, okay, because this R prime will be different from this R. Okay, the R prime will now have 9 carbon atoms, since we want to show that this is a primary alkyl bromide. Okay, so you get this here. So the acetylide reacting with a primary alkyl bromide to get to the terminal alkyne, which is this right here. Okay, now the next question is, how do you get the acetylide ion? Okay, oh yes, okay, yes, Chelsea already given us the answer. Excellent. Okay, Chelsea has given us the answer here. So Chelsea said we could simply just do this. Keep in mind we are going back to acetylide, to acetylene to do this. Take sodium amide. In ammonia, you react that with acetylene and that will get to the acetylide anion, okay? And then the acetylide will now react with the appropriate alkyl bromide, and then to give you the terminal alkyne, which is this here, and then the terminal alkyne will react with borane, followed by hydrogen peroxide to give you your final product, the aldehyde. Okay, so you can see here, for you to do a synthetic problem, you need to know those individual reactions. And that is why I generally start this session by using, starting with the reactions and the reagents in order for you to sort of break the ice and before we get to more difficult problems. Okay, if you follow that, give me a happy face. If you follow that, give me a happy face. Okay. Keep in mind, all we've done is simply just go backwards because we were supposed to start with acetylene, and then of course this is acetylene that we're starting with. This is acetylene, and then we went backwards, and we went backward from the product to the starting material, and that is how we did it, and we call this retrosynthesis. Okay, so let us go to the next one. This was 12, about 13. Let me go to 13. Okay, Dominic, can you go ahead and read question 13 for us, if your mic is working?
Outline a reaction scheme to show how you will synthesize one hexadecanol.
Dominic,
starting from the
if your mic is working, can you read 13 for us? Okay. If it is, oh, it is not. Oh, it is possible to make the triple bond into a double bond and then create the. Oh, Dominic is asking me. Yes. Okay, thank you very much. That was Dominic. Okay, very good. So what this question, this is another question dealing with a synthetic scheme. So what it says is, outline a reaction scheme to show how you will synthesize one hexadecanol starting from acetylene. Okay? Okay, Dominic, this will answer the question you just asked me. Okay, this will answer the question you just asked me. So in this case, once again, we want to start with acetylene. And we want to make this product here, one hexadecanol. So this is a 16 carbon molecule, and at the end of it, you have a primary alcohol. So let us use the bond line formula here to write the structure of this here. Okay, 16 carbon molecules. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and then, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I hope my number is right. Anyway, so this is the one hexadecanol. Let me number this so that I know that I'm right here. This is 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oh, I got one too many. Let me take that out. Oh, hey, I don't want to erase it. So I got one too many. If I erase it, I will take everything out. So, folks, imagine that this is not here. Okay? Okay, so that is 16. So if I erase it, it will erase everything in there. Okay. Okay, so that is our molecule that we need to make. So the question is we need to also now do a retrosynthesis because we want to go back to acetylene. Okay, can anybody tell me if we have to do retrosynthesis for this product, can anybody tell me what single reaction would you perform in order to give you a primary alcohol? What single reaction would you perform in order to get a primary alcohol? Can anybody tell me what reagent you need to do that? Okay. Okay. Anybody? How do you make a primary alcohol? How will you make a primary alcohol? Okay. Okay. Yes. Very good. Excellent. So Dominic said borane. Yes, but you could do borane with carbon-carbon double bond, and that will give you an anti-Markovnikov addition of water. That is correct. So let us write that here. Okay, let me go ahead and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so if you want to do that, you need to put a double bond here. Okay, and then you say you want to use borane. Step 1, BH3, and then you follow that up with hydrogen peroxide. So folks, you can see here, you need to know those reagents and what they do. Okay, so this reagent here, borane followed by hydrogen peroxide in basic medium, what it does is to add water across the carbon-carbon double bond, in other words, hydrogen and hydroxide across the carbon-carbon double bond in an anti-Markovnikov addition. Okay, anti-Markovnikov addition. Markovnikov addition of hydrogen and OH, okay, across the carbon-carbon double bond. Okay, so that we get that. Very good. Now then the next question is, how do we make what one reaction can you perform to give you a carbon-carbon double bond? Okay, what one reaction can you perform to give you a carbon-carbon double bond? Okay, we now want to form our carbon-carbon double bond. Give me one reaction that you could perform to give you a carbon-carbon double bond. Okay, I'll give you a hint. You could start with an alkyne. What reagent do you need to do that? Okay, hydrogen and Grignard. Very good. You could use Grignard catalyst. Very excellent. Excellent. You could use Grignard catalyst. So at this point, I'm going to use an R group to represent the long alkyl chain. So we say we could have this. So I'm going to use an R group to represent the long alkyl chain. If you do that, you do hydrogen, or you just say Grignard. Okay, what Grignard will do with hydrogen is to transform a carbon-carbon double bond into a carbon-carbon triple bond into a carbon-carbon double bond, and that is what you have here. Okay, so Grignard will transform this alkyne with a carbon-carbon triple bond into a carbon-carbon double bond. Keep in mind that this part of the molecule, this is our R group right here. Okay, this is the R group. Okay, very good. So we are getting close. Now, keep in mind we have to go back to the alkyne. Now, how do we make the terminal alkyne? We did that already. Okay, how do we make this compound here? The terminal alkyne. Okay, how do we make it? Okay, we do that. Okay, very good. So now what we do, we simply take here, then let me use an R group again. Say R, use an appropriate, let's call this R prime, because this R prime will be different from the R. So we use an appropriate alkyl bromide, primary alkyl bromide, and then we react that with acetylide ion. And that will give the terminal alkyne. And then from the from the acetylide ion, I know you guys already know that this here, from okay, so you use your sodium amide in ammonia. That would take an acetylene, which is this here. We were supposed to start with acetylene. Okay, to the acetylide ion. And then the acetylide ion will now react with the appropriate primary alkyl bromide to get the terminal alkyne, which is this here. And then the terminal alkyne reacts with Grignard to give you the carbon-carbon double bond. And then the carbon-carbon double bond is reacted with a borane followed by hydrogen peroxide to give you your final product, which is this here. Okay, so you can see here, these problems are fairly easy once you know your reagent. That is why I keep saying this. You need to know what those reagents do, because without knowing what those reagents do, you cannot do any synthetic problem. Or sometimes you may not even be able to do reaction mechanism. Okay, so let us go to, that was question 13. Let us go to 15. Okay. Okay, Ayana, can you go ahead and read question 15 for us?
Outline a reaction scheme to show how you would carry out the following transformation
Diana is having
via a Grignard reagent.
Dominic, can you go ahead and read question 15 for us, if your mic is still working?
Outline a reaction scheme to show how you would carry out the following transformation going via Grignard reagent. Show the reagents needed in each step.
Okay, very good. That was Dominic. Thank you. Okay, once again, this is a synthetic problem. You notice that synthetic problem, the major part of your exam will be doing a synthetic problem. And so therefore, if you know your reagents, okay, thank you. If you know your reagents and what they do, you will have no problem with this exam, because I will guarantee you close to 80% of your exam will have been covered by reagents, reactions, and synthetic scheme. Okay, so what do we have here? We have, what they want us to do is to start with this alcohol here, primary alcohol, and make this tertiary alkyl chloride. And then they also say that you must use a Grignard reagent. That is the limitation here. Outside of that, there is no other limitation, okay? So what do you need to do again? What do we need to do again? We need to do a retrosynthesis, okay? Do a retrosynthetic scheme going from the product, going back to the starting material. Okay, so let me ask you this. Okay, now we need to make this tertiary alkyl chloride. What single reaction or reagent can you use? What kind of starting material and reagents can you use to get this tertiary alkyl chloride? Anybody has an idea? Anybody has an idea? Okay. What single reagent or reaction can you use to make this product? Okay, HCl and ether. Very good. Dominic said HCl and ether. That is correct. Okay, that is correct, but HCl and ether with what? What class of compound? HCl is correct, absolutely correct, but with what class of compound? We are almost there. Keep in mind we are dealing with a tertiary alkyl chloride. Okay, so we are going to use a tertiary alcohol. Ayana said tertiary alcohol. Excellent. Okay, so let us see what we can do here. So therefore, you take that one reaction, you say you want to use HCl with tertiary alcohol. So our tertiary alcohol will have to be this here. So we have to take that tertiary alcohol. Okay, so we take this tertiary alcohol and we react with HCl to get the product. Fine. Okay, then the next question is, how do you get the tertiary alcohol? Keep in mind you have to use a Grignard. Okay, let me also give you a hint. You know, you have a tertiary alcohol. Notice that in the tertiary alcohol, you have 3 different alkyl groups in that tertiary alcohol. So therefore, you cannot start with an ester if you are going to use a Grignard reagent. Because if you start with an ester using a Grignard reagent, 2 of the alkyl groups must be the same. So you cannot use an ester. So that is just a hint. So therefore, what do we need to do here? Okay, we want to form this tertiary alcohol. Okay, what kind of Grignard do you use, and what kind of other starting material do you need? A ketone. Excellent. Okay, Kessler said ketone. Very good. You need a ketone. So therefore, if you are going to use a ketone, keep in mind since there was no limitation on what material to start with, I will just use the, I will take the simple, yes, go ahead. Somebody's trying to ask me a question. Dominic, go ahead. I can hardly hear you, right? Okay. Now, so what we need to do here, we want to form a tertiary alcohols, but keep in mind since you are not limited by the number, by the type of starting material, if I was you, I would use the simplest starting material that I can get. Okay, I say I'll go to, take this back. I will say I'll take this. If you guys can hear me, can you give me a happy face? If you can hear me, give me a happy face. Okay, very good. I lost my internet temporarily. Okay. Before I lost my internet, what I was trying to tell you, that in this case, what I would do, I would start with a very simple Grignard reagent. In this case, I would simply start with methyl magnesium bromide as my Grignard reagent. And because I do want to introduce this methyl group right here, okay? And if you are going to do that, since Ayana also told us that we need to use a ketone, then I will use this. We have to use this ketone. You have to use this ketone. better than that. Use this ketone here. Okay, so you take this ketone here, you react this ketone with methyl magnesium bromide, and then you follow that up with, this is step 1, then step 2, you add water or dilute acid. That will give you your tertiary alcohol, which is this here. And then, of course, I believe that is the end of it. They told us we need to use a Grignard reagent. So this is a fairly simple problem indeed. Let me put everything back in focus. Okay? Okay, so what we have here, since we were not limited by the number of carbon in our starting material, so what we did, we started with this ketone here. React that with our methyl magnesium bromide. Okay, and that would therefore give us this tertiary alcohol. And once you get that tertiary alcohol, you simply now react that with hydrogen chloride gas, and that will give you your final product, which is this here. Okay, now if you follow that, give me a happy face. Give me another happy face if you follow that. Okay. Okay. Okay, so now I think we spend about over 1 hour now. Let's spend about 10 more minutes. Okay, so we've done 15 already. Let me go to 17. Let me go to 17. But I want us to do some spectroscopy. Okay.
What is the expected
Ayala, if your mic is working now, can you go ahead and read 17 for us? Okay, thank you. Okay, so this is a very simple question dealing with a proton-nmr. Okay, proton magnetic resonance spectroscopy. Okay. What they're asking for is the multiplicity. Let us start with, let me go ahead and number this so that we know what we are dealing with. Let us call this here, let's call this 1. Let's call this 2. Let's call this 3. Let us call this 4. This becomes 5. And finally, this becomes 6. Okay, what is the multiplicity of the hydrogen in 1? Anybody has an idea? Multiplicity of the hydrogen in 1. Doublet. Very good. Excellent. That is a doublet. So this is a doublet. Okay, what is the okay, it is a doublet because these 3 hydrogen here, they are only seeing 1 hydrogen on the next carbon atom, and that is why it is a doublet. And don't forget your n plus 1 rule. Okay, where n is the number of hydrogen that it is that is seen, and then if it is seeing 1, you simply add 1 more to it, so that becomes doublet. If it is seeing 2, then it becomes a triplet. So in this case, this set of hydrogen here only see 1 other hydrogen on the adjacent carbon atom, or on the next carbon atom. So that is why it is a doublet. However, the hydrogen on 2, what is the multiplicity? What is the multiplicity on the septet? Excellent, excellent. So that would be a septet. This would be septet because this hydrogen on 2 here is seeing 6 other hydrogen, and so therefore 6 plus 1 equals to 7. and that is why we have a septet. Okay, very, very good. About the hydrogen on 3. About the hydrogen on 3. The hydrogen on 3. What would that be? Hydrogen on 3. What would be the multiplicity? How many hydrogens are they seeing? What would be the multiplicity? Okay. That would be a singlet. Very good. That would be a singlet because this hydrogen here, they do not see any hydrogen on this carbon. Okay, very good. If you can hear me, give me a happy face. If you hear me, give me a happy face. Okay, very good. Okay, how about the hydrogen on 4? What will be the multiplicity of the hydrogen on 4? Multiplicity on the hydrogen on 4. What would that be? Triplet. Excellent. That is a triplet. Because this hydrogen on 4 here, right here, they are only seeing 2 hydrogen, which is here on the next carbon atom, and therefore 2 plus 1 equals to 3, and that is why you have triplet. 2 plus 1 equals to 3, and that is why you have a triplet. Very good. Okay, so the 4 is a triplet. How about 5? The hydrogen on 5. The hydrogen on 5, what would that be? The hydrogen on 5, what will it be? Okay, the hydrogen on 5 is seeing 5 hydrogens. Okay, sextet, very good, excellent. Because it is seen, so this here will be a sextet. Because this hydrogen on 5 here, this here, okay, they are seeing 2 sets of hydrogen, 3 here and 2 here, okay? And 5 plus 1 equals to 6, and that is why we have a sextet. Okay, very good, very good. Okay, finally, about the hydrogen on 6. About the hydrogen on 6. What would be the multiplicity on the hydrogen on 6? The hydrogen on 6, what would be the multiplicity on this set of hydrogen here? Okay, triplet, exactly. To be a triplet, very good, excellent. That would be a triplet. Because those 3 hydrogens are only seeing, these 2 hydrogens here, therefore 2 plus 1 equals to 3, and that makes it a triplet. Very good. So let us do the last question, which is question 19, and then we will call it a day. I think we've done very well today. Really done very well today. Okay, so, okay, let us see here. Anybody just pick up the mic and read this question for us? just pick up the mic and read this question for 19. Okay, let's see. Kessler, if your mic is working, can you read question 19 for us?
Determine the structure of the compound with
okay,
one H264.
Kessler's mic is not working. Ayala, about you, can you read question 19 for us? Okay. Okay, well, thank you, Ayana. I see you are having a little problem with your mic there. Okay, now the question here is, okay, thank you. Okay, the question here is, determine the structure of the compound with the proton-nmr spectrum shown below. Assign the chemical shifts to each set of protons. The compound has a molecular formula of C7H7 with a bromine atom. Okay, this is the molecular formula for that molecule. Now, this is a fairly simple problem to deal with. Here, of course, they have given us the this chemical shift. The chemical shift at 2.31, which is this one here. This here. Okay, they say the ratio of the hydrogen is 1.5. And the chemical shift of this one here at 7.1, the ratio is 1 hydrogen, and finally the one at 7.35, the ratio is 1 hydrogen. When you see this kind of ratio, you know that you cannot get half a molecule. So therefore, what you need to do here is right away by some appropriate integer, you know. I will start off by multiplying by with 2. Okay, so I say, okay, I've multiplied this by 2. So therefore, that means I have 3 hydrogen here. The same thing here, if I multiply this by 2, that means I have 2 hydrogen there. If I multiply this other one by 2, this one here also, I will also have 2 hydrogen. So that is what this is telling you. Okay, so let me erase that. So you could, at this point, assume that here, assume that you have 3 hydrogen responsible for this, based on this information they're giving us here. 2 hydrogen responsible for this signal, and 2 hydrogen responsible for this signal. And that makes sense, because if you look at the formula they're giving us, you have a total of 7 hydrogen in this molecule. And so we do have 7 hydrogen here. Now, the other information that is very useful here, you have a splitting pattern in this region. This is the aromatic region. Okay, the aromatic, those hydrogen attached to the aromatic ring system, they have their resonance in that region between about 7 to 8. So once you see that, that tells you you have a benzene type molecule here. And then, anytime you see this splitting pattern here, what we call a doublet of doublets, you could see the splitting pattern. It's almost as though they are mirror images of each other. That is what we call a doublet of doublets. What that tells you is that you have a benzene that is di-substituted and it is para-substituted. In other words, the two substituents are in the para position. That is what that is telling you. Because this hydrogen here, and this hydrogen here, and this here, what happens here, this and this will be equivalent, and this will be equivalent. And that is why you see this splitting pattern that we see here. Okay, so anytime you see that splitting pattern in your NMR spectrum, then you know that you have a para-substituted benzene molecule. And so therefore, what do we have here? The formula we have is C7. In other words, you only have 7 carbon atoms, 7 hydrogen atoms, and a bromine. So the rest of the molecule is already given. The rest of the molecule is given. So therefore, we could simply say that we only have 1 carbon atom left. So this could be this here, which will be consistent with the 3 hydrogen that we have here. And then the bromine will be here. Okay? And that is consistent with the formula you are given. So this is a very simple problem indeed. Of course, the TMS is the internal standard. Okay, if you follow that, give me a happy face. If you follow this, give me a happy face. Okay, in other words, the structure for this here, the structure they are asking us to give is this molecule right here. Okay, so that is the structure. Okay, now they also told us to assign to give the assignment. Okay, the methyl group that is here. This methyl group, that is the signal. This is this signal right here. Okay, which is about 2.31 parts per million. Okay, and this hydrogen here. This hydrogen here and this hydrogen here, they could be any one of these. So that those could be those 2 hydrogen right here. And finally, this hydrogen here, this hydrogen here, and this hydrogen here are equivalent, and they could be this one here. Okay, these 2 hydrogens. So now we have accounted for all of the hydrogens are present in this molecule. Okay, now if this is clear to you, give me a happy face. I think we are, okay, there was a question that we missed, which is question number 15. Okay, so we are almost at the end of our session today. Let me see, 15, 16. Oh no, okay. Yeah, that was me. You guys could do that. That is the reaction mechanism with respect to the Grignard reagent. Okay, anyway. Yeah, go ahead. Okay, somebody said, could you repeat what makes it para? Oh, okay, I understand that 2 multiplexed around 7 and 6 make an arene, but how do we know that it is para? So, okay, excellent question. The question is, how do I know that it is para substituted? Okay, this is how you know. Okay, anytime, let me go to a new page. When you are dealing with the benzene ring, anytime you have this kind of signal, it's almost that they look like mirror image. Anytime you see this kind of signal, almost looking like a mirror image, then you know you are dealing with a para substitution. Okay? So that is how you know that it is para. Anytime you see the absorption frequency in the benzene region, which is generally about, say, close to about 7 to 8 parts per million. Anytime you see a signal pattern that looks like this, then you know that you are dealing with a para substitution. Now, if it is not para substitution, if you have two substituents and it is not para, this is the kind of stuff you see. If it is not para, this is what you will see. Okay, it would look very, very uneven. Okay, as opposed to in the case of the para, in which you have almost like a mirror image of each other. So that is the way you distinguish the molecule. Sorry. So that is the way you are able to tell whether a substituent is also is para or not. Any other substituent, they are very, very ragged or very jagged, not symmetrical signal. Okay, if that is clear to you, give me a happy face again. Okay, folks, we have come to the end of our presentation today. I'm glad that you guys are able to join us. This is the last session we are going to have online, and the next session hopefully will be sometime in January after your Christmas holiday. So until I see you again, coming to you from ABUJA, and wish you luck on your exam tomorrow, and enjoy your Christmas break if I do not see any one of you before then. And of course, in January, I think maybe in February, we are going to start having the online session again. I will be just as here, and of course, you guys will be in different locations in the U.S. Okay, is there any question? Another 5 minutes after the recording is turned off. So in case some of you may have additional questions for me that you want me to answer offline.